The neutron stars can exist isolated, just one star, but they can also exist in a binary system where two neutron stars are orbiting around each other. And this is an interesting situation because this system emits gravitational waves. These gravitational waves we can detect, and in fact we detected the first gravitational waves coming from a neutron star binary system in 2017. This was a very important observation for physics.
Neutron stars are the most compact stars, but black holes are the most compact object in our universe. Imagine that you have a neutron star, which under certain conditions can collapse to a black hole. This can emit gravitational waves. So the project that we are carrying on here in SISSA, leading by Professor Enrico Barausse, it's about neutron stars in modified gravity that we are gonna call dark gravity.
Since its original discovery in 1998, the current accelerated expansion of the universe has become one of the most important problems in theoretical physics. Physicists had to postulate a huge amount of an unknown dark energy that is able, if we assume general relativity to describe the theory of gravity, to explain the expansion of the universe that is currently accelerating. Another possibility is that there is no dark energy, and actually is the law of gravity that needs to be modified at large distances, at cosmological distances. This is the main motivation for our research activity here at SISSA inside the GRAMS project.
Title of the project, of the ERC project that I lead, is Gravity from Astrophysical to Microscopic Scales. Our current understanding of the gravitational force is based on Einstein's general relativity, which describes gravity very well on scales which are intermediate between cosmological and microscopic scales. In fact, we know that on microscopic scales, general relativity cannot be quantized, so it is not possible to reconcile it in an obvious way with quantum mechanics. And on the other hand, on large cosmological scales, current observations predict or show that general relativity is in agreement with the data only if we assume that 90% or 95% actually of the universe is in what we call a dark sector, dark matter and dark energy. So components, matter components that we do not observe. It should be stressed that we have no direct evidence of the existence of dark energy and dark matter. All we know is that, we can just infer the presence of these components from the motion of matter through gravity. So if our understanding of gravity is wrong, then the inference that we obtain from the data would be wrong. So in a nutshell, what the project is about is to distinguish between general relativity with a dark sector and a modification of general relativity on the other side, what we colloquially call in our group dark gravity. So the ERC project that I lead aims to perform numerical simulations of the coalescence, that is the merger of compact objects, black holes, neutron stars, white dwarfs, in theories of gravity that extend general relativity and try to reproduce a dark energy-like phenomenology. That is, they try to reproduce the observations that we currently interpret as due to dark energy via a modification of general relativity.
Neutron stars are among the most complex stars that we know to exist in our universe. They typically have a radius of around 10 kilometers, and they're 1 or 2 times the mass of the Sun. So to give you an idea, this would be equivalent, or a T-Mach of neutron star would have the same mass as the Mount Everest. So neutron stars are the remnants of very massive, supermassive stars collapsing through a supernova explosion. They are very extreme objects. They are very hot, they have an extreme magnetic field, and they also have a strong gravitational field, which is why these are interesting objects for us to study in our GRAMS project. So the merger of 2 neutron stars is an extremely violent event, so violent even that this event gives rise to ripples in the space-time, and this is what we call gravitational waves. So like waves in water, for instance, these waves travel, they propagate. They can propagate towards us on Earth, and we can detect them. The first gravitational wave signal coming from a neutron star binary was detected in 2017 by the LIGO and Virgo observatories. So the LIGO and Virgo observatories are L-shaped interferometers through which a laser is traveling through both of the arms. The laser is reflected at the end by mirrors, and then in the middle of the detector you can detect an interference pattern, which can then be related to the properties of the gravitational wave. So when a gravitational wave passes through these observatories, it changes the length of the arms in different ways. These arms have an effective length of about 1,000 kilometers, and they're measuring an extremely small difference in length. It's about the size of a proton, which is a millionth of a millimeter.
I've always been interested in astronomy since a very early age. I had my own telescope that I used to gaze at the sky. As I grew older, I realized that I was not only interested in observing the universe, but I was interested more in understanding the workings, so in understanding the laws behind the behavior of the universe as we observe it. And this is why I ended up studying physics. At that time I was more interested in cosmology, so the study of the universe on very large scales. But then when I moved to Trieste, to SISSA, for my PhD, I got more interested in smaller scales, so more astrophysical scales, and in particular I got interested in gravity and in gravitational waves. After my PhD I moved, I was outside Italy for many years, working again on gravitational waves. I was in Maryland, in the US, I was in Canada as a SITA National Fellow at the University of Guelph in Canada. I then moved to Paris, where I stayed for 7 years. And then after getting this ERC grant, I moved back to Trieste, where I did my PhD, after a hiatus of almost 11 years. So in a sense, it's a full cycle from that point of view. So I'm very lucky to have a very diverse pool of very bright collaborators. So there are people in my group who come from the Netherlands, from Mexico, from Chile, from Germany, from Hungary, from as far as Argentina. And I'm also very lucky to have very bright external collaborators who are not formally part of my ERC projects. And in particular, Carlos Palenzuela, Professor Palenzuela at the University of Balearic Islands in Spain, who's an expert about simulations of compact object binaries, without whom this project wouldn't have been possible in the first place.
I am Marcelo Rubio. I'm 30 years old and I am from Argentina. In particular, my work aims to have a better understanding on how is the physics of fluids and how is the matter dynamics surrounding a wide range of compact objects as black holes, neutron stars, and even what stars are made of in their interior.
Okay, hello, my name is Sebastian Völker. I'm a postdoc here. I'm from Germany. So in my work I focus on the oscillation that compact objects can have. So these are black holes and neutron stars, and we want to understand these objects better by looking at their characteristic frequencies and that they emit when they're excited. You can think about them like instruments that you start to play. Different instruments have different sound. And we want to understand basically the structure of these instruments to get more insights about nuclear physics, for example, when we study neutron stars, and testing general relativity as theory of gravity when we look into black holes.
I'm Matej Bošković. I'm from Serbia, which is like 6 hours to the east of Trieste. Before enrolling a PhD course in SISSA, I already knew Enrico and his work because I did my master thesis in a similar topic. So I've been working on like 2 topics. Boson stars, which are hypothetical objects connected to some dark matter models. So I've been exploring some of their properties and how can we distinguish binary systems with these boson stars with contrast to binary black holes, for example. And the other projects is more related to the topics that others are pursuing. Modified theories of gravity, how can we how can we understand some of these theories and contrast them with general relativity.
So I'm Nicola Franchini, and I work as a researcher in studying black holes and neutron stars in modified theories of gravity. In my current research, I'm studying the perturbations of black holes and how these perturbations behave in different theories of gravitation. Because one of the things that the gravitational scientists are trying to understand is whether the theory of Einstein of general relativity is the correct theory to describe compact objects or not.
I joined the group in September. Before that, I was doing my PhD at the University of Cambridge in the UK. So coming to Trieste was a little bit of change. The weather is definitely much better here. Food is also much better. So my name is Áron Kovács. I'm from Hungary, and I'm a mathematical physicist. There are some arguments and little signs suggesting that Einstein's theory is not the complete story. So our group focuses on studying alternatives to Einstein's theory and testing these theories observationally. And so my role is to explore mathematical properties of these theories and find necessary and sufficient conditions for these theories to make them predictable and giving us the opportunity to make observational tests on these theories.
So my name is Lotte ter Haar. I come from the Netherlands and I'm a PhD student in the GRAMS group here at SISSA. So the work I do is a bit mixed. I collaborate with a couple of postdocs here in the group, and some days it can be numerical simulations, other days it can be more analytical calculations. But it's a bit of both, but always about the same topic, and we try different approaches.
My research field is numerical relativity, which means, in simplest words, solving the Einstein equation in the computer with supercomputers. I am studying compact objects like coalescence of black holes, neutron stars, or even something more exotic like boson stars. And the reason that I am doing these projects, or I am working in numerical relativity, is because my dream was to put the Einstein equations in the computer.
The most difficult part when you modify gravity at large distances in order to explain the accelerated phase that we see today is that general relativity is tested very well at local scale, in the solar system, at even at galactic scales. So to modify gravity at cosmological scales, the modification has to be hidden here, in the Earth, in the solar system. And for this reason, physicists proposed a new mechanism that is responsible for hiding these extra forces that we don't want to see in the solar system scales because we don't measure them. Some kind of screening mechanism is needed in order to avoid modification where we know GR works very well.
Compact object mergers are the ideal tool to explore the differences between general relativity and its extensions for many reasons, because they involve very strong gravitational fields. They involve velocities which are close to the speed of light. So it's a regime in which gravity is more extreme, and a regime which hasn't been tested very much so far, exactly because gravity is so extreme. We cannot find these conditions on Earth. So the idea is to make predictions for the behavior of the merger of these objects, and in particular for the gravitational waves that they emit in both general relativity and in extensions of it, what we call sometimes in our group dark gravity. In the end, we ended up producing these simulations, and we find some unexpected results. So we find that indeed the merger of two neutron stars, which are the densest stars that are known to exist in the universe, behaves in a slightly different way in general relativity and in dark gravity. In particular, the merger of two neutron stars happens slightly more quickly in the presence of dark gravity. And this could be used as a tool to really distinguish between general relativity and dark gravity. Of course, we cannot do it yet with current observational data, but we hope that with next generation gravitational wave detectors, such as the Einstein telescope, we will be able to tell the two apart, and therefore tell if really dark energy exists or if it is just an illusion due to our incomplete understanding of gravity on large cosmological scales.
So in order to study this system in the very strong regime of gravity, we need to solve the Einstein equations, but not just solving analytically, let's say, or by doing some kind of approximation. We took the equation and we solve, but we solve with a supercomputer. The steps for performing a numerical simulation in my opinion, are the follows. So first, you take the equations, then you write down the equations in such a way that you are able to put in the computer. Then the second step is choose your physical problem. We choose dark gravity, which are these neutron stars in this alternative theory of gravity. Then you study the problem by performing some simulations, easy one. For example, isolated stars, you study its evolution. Then you perturb a bit the stars and see what happens. And the final step, you take two stars and make the coalescence. This kind of simulations that we did, it took like 3 months for one binary. After months of work and simulations, we managed to publish this work in a very important journal, which is called Physical Review Letters. We are super excited about our results because it was the first simulation in this alternative theory of gravity.
So the time scale to reach a conclusion on whether general relativity or dark gravity is preferred by the data, unfortunately, is not very short, so we need suitable detectors of gravitational waves that extend to low frequencies. And one such possible detector is the Einstein telescope. This is a European gravitational wave detector that is currently scheduled to be operational by the, say, mid-2030s.
Imagine that we have a binary of neutron stars about the merger. This merger in the dark gravity can lead a new emission called quadropolemisia. This quadropolemisia can be detected by either Einstein telescope or LISA.
So despite the incredible accuracy of the LIGO and Virgo observatories, a new generation of gravitational wave observatories is already on the way. In the future there will be the Einstein telescope and also the Cosmic Explorer, which will be able to probe different types of objects than that the LIGO and Virgo observatories did and still do. Another type of observatory that will be launched in the future is one that's not based on Earth, but will be in space. This is, for instance, the LISA detector. And these are 3 detectors, in fact, and they're traveling around in the shape of a triangle with a distance of 2.5 million kilometers between the detectors. And with this detector, we can also see different types of gravitational waves coming from different types of objects in our universe.
Yeah, of course, this begs the question of what we'll do in the next 10 to 15 years. So we're not planning to stay idle and do nothing. So far, we performed just a handful of simulations of binary neutron stars in dark gravity. So we plan to extend the number of simulations we perform to understand the effect of dark gravity even better. We plan to extend these simulations to even lower frequencies, so longer simulations. We plan to extend these simulations to other systems of compact objects, in particular black holes. Of course, if we were to detect a deviation from general relativity, physics would be shaken at its core, because really gravity, and general relativity in particular, is the outlier in the group of 4 fundamental forces that we know of. In particular, we know that general relativity is hard to reconcile with the other 3 fundamental forces. In particular, it's hard to quantize general relativity. So if we were to detect a deviation from general relativity, and if we were to confirm specific alternative theories to general relativity, that might have implication for the quantization of gravity, so the unification of gravity with the other fundamental forces. So it would have a realm, a plethora of consequences, mainly for our understanding of physics and our understanding of the universe. So I can't exclude that in centuries from now, our understanding of gravity, not only our work, but the work of the whole community that today is looking at the workings of gravity, will have practical implications.